Let's consider propene-propane separations. Most of the available adsorbents are selective to propene, and therefore the desired propene product can only be recovered in the final vacuum blowdown stage. Here is a typical PSA scheme for propene-propane separations described in the paper by Khaligi. The 5 stages consist of pressurization, followed by an adsorption cycle in which propane is removed from the top of the column. The adsorption cycle is followed by a co-current high pressure purge with propene in order to remove any adsorbed propane in the pores. This is followed by a co-current blowdown step, and finally a countercurrent vacuum blowdown is used to recover propane of the desired purity. The product purity is dictated strongly by the amount of propane that is still present in the void volume and in the pores in this final countercurrent vacuum blowdown step. Therefore, it is important to have an adsorbent material that completely rejects propane into the gas phase and is highly selective to propene. One such material is Chabazite, and that is the material also described in detail in this paper. Here's the structure of Chabazite. Consists one unit cell of Chabazite has 6 cages. Each cage is separated from an adjacent cage by narrow 8-ring windows. But the cage volume for Chabazite is slightly larger than for DDR zeolite, but significantly smaller than for fugicite. Chabazite zeolite, suggested as an adsorbent for propene-propane separations, is a cage-type zeolite where adjacent cages are separated by windows which are 4.2 angstrom in this direction and 3.8 angstrom in this direction. Due to subtle differences in the bond angles and bond lengths between propene and propane, the ratio of diffusivity of propene to propane is a few orders of magnitude high, as reported in this paper by Ruthven and Reyes. And therefore, due to the high ratio of diffusivities, it is possible to construct a kinetic separation scheme for propene-propane separations. For kinetic separations to be effective, diffusional influences should be strong enough, and the diffusional influences are dependent on the size of the crystals of zeolite or MOF that are embedded within the adsorbent pellets that are packed into the fixed bed. I illustrate the influence of particle size and in particular the radius of the crystallites R sub C on kinetic separations of 50-50 mixtures of propene and propane using Chabazite zeolite. The fixed bed adsorber operates at a temperature of 353 Kelvin at a total pressure of 2 bars. For theoretical background, consult my paper published in ACS Omega 2019. The material I'm going to present today is a follow-up to my presentation titled Diffusional Time Constants and Contact Times, that is available for viewing on my YouTube channel. I consider a fixed bed adsorber with a length of 0.3 meters and the voidage of the packed bed is 0.4. The superficial gas velocity at the inlet to the fixed bed is 8 millimeters per second, and the interstitial gas velocity, which is the superficial gas velocity divided by the bed voidage, epsilon, is 20 millimeters per second. This yields a contact time between the gas mixture and the particles of 15 seconds. For propane diffusion inside the crystals of Chabazite zeolite, the ratio of diffusivities of propane to propane is 5,000. And to highlight the influence of the size of the crystallites that are embedded within the catalyst pellets, I consider 4 different scenarios with 4 different particle sizes, which are increasing from A, B, C, and D. Instead of focusing on the particle size, I vary the diffusional time constant for propene, which is the Maxwell-Stefan diffusivity for propene, divided by the square of the crystallite radius. And in the first scenario, A, we have D1 divided by RC squared of 6.8 times 10 minus 2 per second. This is reduced to 1.7 times 10 minus 2 in this case, to 6.8 10 minus 4 in this case, and 1.7 10 minus 4 per second in this case. Increasing the particle size or the crystallite radius results in stronger diffusional influences as we move from A to B to C to D. And the influence on the component breakthroughs plotted on the y-axis is the dimensionless ratios of the concentration exiting the fixed bed adsorber divided by the inlet concentration, Ci divided by CO naught, and this is plotted as a function of a modified time parameter, which is Q naught, the flow rate of the gas mixture, the inlet, in units of liters per second at the actual temperature, 353 Kelvin, and actual pressure, 2 bars. This Q naught flow rate value is multiplied by the time in seconds divided by the kilogram of zeolite, in this case Chabazite, that is packed inside the fixed bed. This is a convenient modified time parameter. We note that with increasing diffusional resistances, the breakthrough of the saturated alkane C3H8, plotted in blue, occurs progressively at earlier times, and the time interval between the breakthroughs of propane and propene is larger. Now, earlier breakthroughs are beneficial for the 5-step PSA scheme that I had described earlier, because the saturated propane is virtually excluded from the pores, and this is important in the achievement of high product purities. So the important takeaway message from these simulations is that for kinetic separations to be effective, we need to choose the particle size carefully, and the diffusional influences should be strong enough to lead to large differences in breakthroughs times for propane and propene. There is another important factor that determines the strength of diffusional influences in kinetic separations, and that is the contact time between the gas mixture and the zeolite or morph that is packed within the tube. I consider a set of 4 simulations for a fixed bed of length 0.3 meters in this is the length of the packed bed, the bed voidage of 0.4, and the crystallite size is held constant such that the diffusional time constant for propene, that is the Maxwell-Stefan diffusivity for propene divided by the square of the crystallite radius, is 1.7 10 - 4, and the ratios of the diffusivity of propene to propane is constant at 5000. By varying the gas velocity at the inlet, we can examine the influence of contact times on the separations. I consider 4 scenarios, A, B, C, and D, wherein the contact times are reduced from 30,000 seconds to 3,000 seconds to 300 seconds to 15 seconds. We note that if the contact time is very large, then the separations are dictated by mixture absorption equilibrium, and diffusional influences are of negligible importance. And we see that both the components propene and propane break through at approximately the same time. As the contact time decreases, the saturated propane breaks through earlier than the unsaturated propene. And with decreasing contact times, the breakthrough of C3H8 occurs progressively earlier, and the time interval between the breakthroughs of propane and propene is larger with decreasing contact times. So from these simulations, we conclude that the choice of the gas velocity or bed diameter is quite important in kinetic separations, and the contact time for a given particle size needs to be short enough for diffusional influences to become effective and optimal. Watch also my previous presentation, diffusional time constants and contact times, on my YouTube channel.